I'm Carolyn Matl from UC Berkeley's Heart Lab, and I'll be presenting our work on deformable elasto-plastic object shaping using a new elastic hand and model-based reinforcement learning. Soft robotic end effectors are useful for interacting with delicate objects like coral reefs and wine glasses due to their low intrinsic stiffness and mass. In our prior work, we designed a variable stiffness soft end effector called Stretch, which enabled new robotic manipulation capabilities with deformable solid objects. Its compliance was crucial for handling soft elasto-plastic objects like dough without permanently deforming or flattening them, while its ability to controllably vary in stiffness allowed it to estimate a proxy for object stiffness as well as modulate the force it exerted on the object. In that work, we demonstrated that this new end effector design could be used to roll a block of Play-Doh into a sphere. However, the algorithm used to roll the dough was heuristic, in that the robot just applied the same rolling action to the dough until the goal condition was met. Because this was a simple heuristic algorithm, completing the task sometimes took a long time, even on the order of 20 minutes. But when we compared this with human examples of dough manipulation, we knew that this problem should be solved more efficiently. And this is exactly what this work set out to accomplish. We set our goal to efficiently roll a ball of dough into logs of varying lengths. To the best of our knowledge, this is the first work to propose a solution using a soft end effector to shape servo a deformable elasto-plastic object. Our main contributions are thus as follows. We designed a novel elastic end effector attachment that is cost-effective and easy to integrate with a parallel jaw gripper. The elastic end effector is also used to estimate the stiffness of different dough, which improves rolling performance. We also presented an algorithm leveraging model-based reinforcement learning and simple featureization and actions that enable tractable optimization for real-time solid deformable object manipulation. And lastly, a series of robotic experiments rolling dough of different hydration levels into varying lengths serve to quantify and demonstrate the efficacy of the proposed hardware and software framework. In this work, we revised the design of the original Stretch end effector to compensate for kinematic limits required of the dough rolling task. We made the entire end effector attachment out of elastic bands, and as you see here, it's much slimmer than the prior version. The depth camera was also fixed at an overhead position instead of being rigidly attached to the robot arm. Notice that this task requires the interaction of a deformable end effector with a deformable object, so this involves highly complex and high-dimensional dynamics that are difficult to model. So instead of explicitly representing the dough-to-hand interactions, we use model-based reinforcement learning to learn a transition function for these interactions, meaning we learn from data the relationship of, given an action applied to the dough and its current state, what will the dough state be after that action is applied? So this model is represented by F. Now within this framework, we use model predictive control to select the best action to take at this time step given the current state of the dough. This is done by optimizing the cumulative expected reward over a certain number of time steps into the future. So we're looking ahead where at each time step, reward is calculated as simply, in this case, well, how close is the dough to the goal's shape? And what the reinforcement learning framework adds to model predictive control is that it allows us to iteratively update or improve the transition model F to better reflect the dynamics of the dough and hand interactions. This means that if we start off with the wrong model or a poorly initialized model, then the algorithm can still self-correct. Now, one might wonder at this point, how does the robot deal with such high-dimensional data since these interactions are highly complex? Well, with some intentional engineering, we can simplify the problem to make it a lot more tractable. In our case, to simplify the state space of the dough, we took the dough formation's bounding box and used those dimensions to track the dough's shape progression over time. As for what actions to apply to the dough, well, the two things we decided to vary were the stiffness of the hand's elastic membrane, which we could vary by stretching or closing the gripper, as well as the depth at which the robot pressed the dough. These two parameters directly affect the load force imposed by the elastic hand. The rest of the robotic action was fixed in that each roll consisted of a back and forth motion at the highest point of the dough formation. And given all these simplifications, we were able to train a dynamics model of these interactions with only about 1 hour of robot time, where the robot randomly interacted with a ball of dough under these action constraints. For our first experiment, we compared model-based reinforcement learning using iterative random shooting with refinement, along with simple direct numerical optimization of our objective function, against a random action selection policy as well as a heuristic baseline policy. Each action selection algorithm was subject to the same action constraints defined earlier. We can see here that comparing the reinforcement learning methods with the random and heuristic policies, the robot was able to roll the dough out into the 6-inch log with significantly fewer rolls. Using model-based reinforcement learning with numerical optimization, the robot also demonstrated efficiently rolling the dough into different lengths, ranging from 2 to 12 inches. However, what happens if the dough that is being manipulated now isn't the same dough as the one that was used for training? So maybe it could be drier, which would cause it to be less malleable and stiffer. And this is actually a very realistic scenario since the material properties of dough can change quite quickly. Well, because this model-based reinforcement learning framework allows the robot to iteratively improve the dynamics model given new observations as the robot interacts with the dough in real time, we show in our second experiment that it's able to self-correct and efficiently roll out a stiffer dough much faster than compared to when using a fixed model with just model predictive control. We concluded our experiments by revisiting an idea from our prior work, which was using the stretch end effector to estimate a proxy for the stiffness of deformable solid objects. So this proxy value for stiffness is estimated via active palpation, where the estimated load force of the elastic membrane is divided by the detected amount of deflection experienced by the object upon contact. So for this work, we wanted to use these estimates to calibrate a model for dough-to-hand interactions to improve the efficiency of the dough rolling task. By using stiffness measurements to interpolate between predictions from two different models, which were pre-trained on a stiff dough and a soft dough, we showed that stiffness estimates do indeed help the robot regress to a better dynamics model for the dough interactions, and this leads to significantly more efficient rollouts. If the robot sensed that the dough was soft, it would use a different rolling technique than if it sensed that the dough was stiff. For instance, for a hard dough, the robot chose to apply actions that corresponded with higher force output. In comparison, for the softer dough, the robot chose to initially apply low force to the ball until it formed into a short log, and then it gradually increased the membrane stiffness to finish rolling the ball out into a longer log. So to summarize, this is the first work, to the best of our knowledge, that performs deformable manipulation using a soft end effector on elasto-plastic dough. We present a novel end effector that is not only cost-effective and easy to integrate with a parallel draw gripper, but it's also able to vary in stiffness, allowing it to effectively manipulate soft deformable objects like dough. We then leveraged a model-based reinforcement learning framework to roll dough into different lengths, where simple featureization and actions enabled tractable real-time optimization. Real robot experiments demonstrated high efficacy of the percentage system, where the proposed action selection method exceeded the heuristic method by more than 60% in efficiency, and where stiffness estimation enabled better model initialization, which consequently improved the robot's performance by approximately 40%. We hope these experimental results can inspire more work in the area of deformable solid object manipulation. We're interested in exploring, via future work, new low-dimensional parametrizations of dough, and to experimentally compare more dough-to-hand dynamic model representations. Ultimately, we hope this technology can be used to manipulate real dough into more complex shapes, such as pretzels. Thank you for your interest in our work, and please see our paper for more details.